So let's wait for somebody else to join. Right now we have very few people online. We'll see. Like I will also put some things together just in background. Let's wait 5 minutes to start. Okay, we can slowly start, and then hopefully others will watch this video later and learn a couple of things. So let's see what I have here. Whiteboard, right? So we'll start first by examining a little bit last time's work before we learn something new. Last time we talked about the convolutional neural networks, which is still the basis for many models nowadays. By the way, I need to double check if you can hear me. Also, I'm not sure exactly how well is my internet here, but hopefully it will be good enough. So can you hear and see okay? And I will, please type in plus minus if there's any problem in the chat. And I will show some of these code examples from people who submitted the homeworks and the classworks, and we'll try to go through some problems which have been arising. I got some email from students that didn't work something. We'll look at that. Just a second. So please type something in the chat if you can hear me, and meanwhile I will try to find what was the task to do. Okay, the batch norm equation and the convolutional network architecture. I'm going to put that on the whiteboard. Okay. Sorry, I still have a little bit of cough. Okay. So yeah, so this is the architecture. So we need to have convolutional layer, batch norm to the ReLU maxpool layer, convolutional, batch norm, ReLU maxpool. By the way, maxpool and convolutional quite similar thing. Batch norm a little bit more complicated maybe. We'll look at that in a second. So that was the task, and also the batch norm equation. last time explained why we need batch norm. So the idea is that in the hidden state, if we don't have batch norm or any other normalization, we will have dead neurons, where the idea is that I have the nonlinearity function, which in 99% of the cases are the rel function. Then if I have if my values have drifted to the left side, to the minus side, then the input on the x-axis will be 0 and the output on the y-axis will be also 0. So all of these things will be just dead forever because the gradient also will be 0. So there is no chance for these features to recover. So that's why with the batch norm we normalize, standardize everything. We put everything, all of the features around the 0. So then at least this part will not be dead because the input will be the same as the output here. Maybe it makes sense, hopefully. So we'll see that is that. Okay, thanks for Niels and people online. Hopefully others will join later. Yeah, anyone who want to do research with these things, please let me know as soon as possible, because this will take some time to get to the level where we can do proper research. But at least if you got so far, you're on the right track. So okay, let's look at this example of the code and maybe the previous one which we did in the class, to see what people have attempt to do and what was the result. So okay, I know there were more than this, but I'm just looking at some of the submissions. So custom convolutional layers, this looks interesting. Forward pass, why would you? Oh, this is very interesting. Basic, right? Okay, this implementation seems very strange because so please base your work on the templates I give you, not create your own code, because this seems to be generated code for sure. There is no context of what we did before, and the syntax is way over your head basically. So this doesn't help anyone. Please don't do this. So this would not be good. Let's look at some other examples. Okay, so this is at least based on the template. That's good. Sorry for my coughing sometimes. Okay, so let's see. Convolutional layer, that's what we did in the class. That's great. Batch norm. Okay, so this is something new and might be complicated, but hopefully not. So there is actually something fundamental here. Okay, let me show you a couple of parts. So first of all, so this is the batch norm function. Again, you have the equation on the whiteboard. So during the training, and this is like critical logical thing to remember forever for these models. So during the training, there is a different way how this works than using the inference, and you change these modes, training and inference, using if you scroll down here, the model eval, model train. This is something that maybe people who start with this don't realize, but every time when you call model train, it goes through all of the torch and layers that are the member variables, which are inherited from torch and n, and set them training true basically, and for the inference it sets training false here with eval, and this is significant because not only the batch norm works like that, there are many functions that work like that. For example, dropout. We will look at dropouts, which are also way to make your models more robust and stable. They also do not work the same way as for training and as for the production inference phase. Please remember this part. This is kind of like a significant part for these models, that even though you train them the similar way here, right, as for the inference, if I scroll down, you just call forward, right, here where you have just forward, right, and then do the back propagation just for the training part. But in this forward does not behave the same way as for the training and for the evaluations or inference mode. That's something to remember, because there will be many cases where that's important. And I think in the whiteboard equation might be listed, or also I gave you the template where it's already hinted how this should work. So, and the other thing which might not be clear just from looking at the code is this part. This part was designed to not calculate the mean and variance every time I call the eval part, but to do this just once. Do this just once, first time when you call eval mode. Sorry, hopefully it will not get too bad with coughing. So the eval mode, just once. Also, I'm just thinking now, maybe I should somehow make this better, because if I would look at this code the first time, I might get confused myself as well. I will just make some mark to my notes that this should be better documented, this idea of that this is just once, called once. To do better document, this is called once in eval mode. And so you are calculating just once the standard deviation and mean, and this is then used for the equation here, the same way as up here. So one thing already, I appreciate this code basically, it, and like really like the person who wrote this understood how this works. This is a good kind of like characteristic already to this person. So, but the one thing you could do is you can see that this equation is the same both places. You could just write it here. I think it should work the same way, and also where, yeah, so just like there. So don't repeat the code where it's not necessary, but otherwise seems really good. I think, like not sure about this line, it's yellow, but should be correct. So this is really good. Good way, like how to implement the batch norm. Great job with that. Max pool, as I said in the lecture, it is like the same code for the convolution, so it seems about the same code. And then here, this part seems tricky. I need to look at this a little bit. So it is always better to write it a little bit different way rather than make code like this. First of all, I already see that this code is a lot less generated than the previous one which I showed. So because normally experienced people don't write the code like this. So because first of all, like if there would be error here, you would not be able to debug it. So and the square bracket 0 makes a little bit of kind of wrong assumption what is there. So this is not actually output of the array, this is something different. So how this works is So let's see. So this will be the max max. So this will be the max max of dimension deepest dimension. So this will be which dimension it will be. So the fourth dimension. Okay, if we call it from the 0, this might be dim3, and the other parameter will be actually max dim index. So, and if I just copy this part here, this would be much clearer way to write this code, much clearer, like that. So this is instead of writing just like that, it's more debuggable and also much clearer. And then from max dim, you would max dim 3, you could have max dim 2 index, and then again also definitely this is a good sign that person wrote it themselves, so because you would not use different function for this, but you could use it. So dim -1 like that, and then if you have this dim, then you could have added here. So what is actually happening here, and I'll try to explain a couple of things. Maybe somebody who's not proficient in Python might get confused. So here the first line, maybe you can visualize this a little bit. So let's let's try to visualize this kernel, which is cut here in some kind of two-dimensional space. So let's say we have some random numbers. So I don't know, I will just type something randomly. So this will be one line. This will be the patch basically. So 8, 9, I don't know, like that. So this is the kernel Xbox patch, for example. So, and this Xbox would be basically in one, like if this is a grayscale, if it's like multi-channel deep in the module, it will have multiple these boxes, but we'll stick to this so it's clearer what's happening here. So, and then if I'm selecting -1 dimension, it means so why I said this is the third and the second dimension, because normally you would have these dimensions, and now we're talking about the height dimension. So this would be, even though it's written height, it would be width actually, but I know I wrote it in that way because it makes more sense having h at the end, but normally arrays are like that. So then what it means now, so we are now liquidating the column values. So after this function, what we will get here, so after this function, what we will get here will be the max value from the column. This is 7, 6, 8. So this is that, and then the last one is liquidating the rows, and now the output will be just 8 basically. So this is the max dim, and then this 8 is placed inside the cell as the maximum value from which I'm looking at. Again, if somebody is confused of what I'm showing here, this is the task, and let me show you the example from last time. We will get to today's session as well. Kind of also try to make sure that you understand previous topics, and also if any questions, write in the chat. I'll try to help. We'll go also to some more examples today with so this is what we're trying to do. And by the way, the maxpool function can work also not only in these nicely divisible squares. It can work also with kernel 3x3, for example, and stride 1, and this could be fully usable maxpool function. Is just that this way it is more controlled. so that I know that the size will be 2 times less than the input, right? So, but it can be any kind of configuration. Okay, so go back here. And just for the Python part, so this part, let's see, did I had it in the convolutional function? Right, it didn't have it that way. Oh, some parts seems in this code that were not generated. Some parts seems about strange, because if I would write this code myself, I would probably copy the same procedure as here using the I out and J out. Of course, I can do that, or I can calculate the position using this syntax. So this syntax, what it means in Python, it is the division without the decimal number. So basically it means that if I have so, and by the way, so this is upper part here. Yeah, this is really, so it, I guess it works, but it's yeah, it's it doesn't feel that this is the same way I showed you. So basically if I have 210 divided by, okay, let's try to make something closer to, so let's say 14 divided by 3, like that, then the output will, okay, so the 12, 15, right, so the output will not be 5, it will be 4. Even though the output is very close to 5, it will be floored down to 4. So this is what's happening here. But again, if I would write this code myself and not use some generational capabilities, I would probably use the out I. So definitely please try to write your code yourself as much as possible, even if you have mistakes. Otherwise it's like kind of hard to learn, right? That you will just generate something and don't understand how that works. So that's that part, but hopefully you get the point about the max pool. So then the architecture, so this seems really nice. Everything that's written here seems appropriate. And then at the end, the linear layer and the softmax is a separate output because there's no learnable parts here. Seems really nice. So this is a very good job. So even though I found some parts which you probably didn't write yourself, this is really good good work. So that's great. So then so this is this. So it seems 2 people just copied the same code, so these 2 are really bad. So please don't do that. I will just get like it might as well get 0 basically. So it doesn't make sense to do this. Please don't do this. So then there is another one. So this was, I think, the class work which didn't work. We'll try to quickly debug how people, if somebody, so if any of you something doesn't work and you try to understand how this works, please send it over to me in email probably, or write at least email that you submitted something that doesn't work, because in the Moodle I do the evaluation, but I basically don't have I cannot follow every single piece of the code. I just picking them up and evaluating together with you and later. So yeah, so please definitely let me know. So, and this piece of code didn't work, at least from the student I understood. So we'll see what's wrong with it. We'll see what's wrong with it. Okay, so that it needs to download the data set, unfortunately. Let's see. Right, sorry for that. Okay, I'll do a different way. I don't want to wait for the download of the dataset. I'll just copy this thing to other screen. Just a second. We'll try to debug this together, and then we'll move to today's topic. Yeah, and if any questions, write in the chat. I will look that up as well in a second. So Right. Okay, sorry for delay. Just want to get down to this issue. PyCharm loading, so I will make a file buggy. Okay, buggy, copy, paste. Okay, so in this folder there should be the dataset. Let's see if I can access it. Yeah, and today's topic, by the way, will be quite fundamental as well. So for many models to come, this will be a very significant way how to build models. So okay, so let's look at the same code as it last time. Right, again, I need to change the environment. Okay, we'll see if I can make this work. Okay, run. Hopefully the dataset will be there. Okay, I already see something strange here. It says, oh, window max. Okay, cool. Right. Okay, great. Excellent. So this code is actually farther away than I thought. So this is also good. So, right. Yeah, and I see that this is something that a person tried to do themselves. Right. So the window, right, you can write it like this. There is some buggy stuff going on here. First of all, like the previous word. So here definitely need to be the bracket. The bracket location is wrong. Then the -1, -1. So this should work, except except this part is a little bit wrong. There should be stride like in the previous word, right? You go over the window of the basically of the input feature map, and then you place just the one value here. So actually the same exact way as for the convolutions. So as for convolutions here, you have the I out, J out, and I and J. I and J is for cutting these windows or boxes, and I out and J out is just one unit ahead, and then placing just this either one number or basically vector here with the channels. And here in the previous example which I showed, where the max pool, those max pool patches, it was just for the visualization. There is actually not just one number, there is the channel dimension. So what I'm placing here, it would be just patch comma channel, right? It will not be just one single value, but for each channel it is single value. So that's what we're doing here. That's why also we have these two colons here, batch, channel, and then place one value for each of those. But this part is a little bit wrong, and the previous example showed how to do this right. Okay, but regardless of that, I want to find where is some other bugs here. So FC, so this bug basically is usually simple to fix, because it says that the calculation of the last layer vector was wrong. Basically, yeah. So, and this, how this could happen is that so here the out channels 18. Oh, there's even more bugs, but I really appreciate this kind of code. Please submit more this kind of code, and don't submit those two copy paste to student generated code which is out of context. Please don't do that. Please do this. So here basically, let me actually maybe share the full screen. Sorry for coughing. I will try to get rid of my cough. Okay, so let's share the full screen just for the sake of making better comments with annotator. Okay, so here some of the mistakes that we can see already. Okay, let's try to annotate. So first of all, we have max pool here, which is good because it's not learnable. Max pool doesn't have any learnable features. So any learnable features like weights, biases, and sometimes also you have prelu, or it's just called like parameterized relu or something like that. Then in all of those cases, you would have you would need to place those variables up here, basically. Like for example, this is FC, right? So fully connected layer. So there is something that I want to learn. In softmax, there is nothing I want to learn. So that's why not often you would add softmax up here. Plus also, you would definitely not make softmax 2D, which is something different that we need here. So this is probably one of the reasons why the calculation doesn't work out. So you don't want to add it here. Also keep in mind, I told you that for the loss functions in PyTorch you have built-in cross entropy function, and built-in cross entropy function actually relies on that you don't use softmax even here. So if you use built-in softmax function, built-in cross entropy function, you would not add even softmax here. It is included in the loss function basically because the derivative is simpler than if you put together softmax with the log likelihood loss. So that's just to keep an eye what kind of functions in what places you place. That makes the difference. So other things, out channels, right? So out channels is this is correct basically. So 18 out channels, this is good. Out size, because this is the square, right? Rectangle, yeah, square, yeah. So the out size, this is correct. Maybe some other part here is not aligned, like max pool for, all right. If the max pool is implemented wrong, then definitely also this would not work correctly. So we'll we'll try to look at that. Okay, let's go back here, put some comments here. At least I didn't had the chance to go in very high detail through all of the homeworks this time. We'll try to do this better in the future, but at least we found one really good work and a couple of bad ones, but this is also not too bad. I at least see that somebody tried to do this themselves. All right, also these are actually not your functions, these are all NN functions, so they must work. There is some bug here. Okay, we'll see. So if I remove just that one, let's see if it works without that one. Run. I will look in the chat in a second. I know I've not paid attention to that for a while. Just need to debug this and show you how to debug yourself this. So yeah, because the person who did this not using their own functions, what I mean own functions, like the other person which I reviewed previously was doing this, right? Their own functions of maxpool conv2d, and they should work the same way basically. So your function should be the same as the built-in one, at least for the behavior part of it. The built-in one will work much faster because many of the parts of the function are compiled in C++ basically. So in size, oh, there's another bug. So the in size is not the channel count. Here should be 28. This should be the size of the image itself, not the channels. Channels is something that we actually don't take in account in this calculation, because channels can be easily projected in higher dimensions or lower dimensions. As I showed you, we can project from shadow and to shadow. So, but the size of the picture itself, the feature map, it's something that we control by using these levers, like the kernel, stride, padding, dilution. There's also like ability to, I will show you. So deletion, sorry, So this is actually also a very cool parameter. So you can have these spaces in between the strides. This is very useful if you have like large images, or I think it was used also for transposed convolutions, if I'm not mistaken, but we'll look at that a little bit later. Okay, so let's try to run again. Okay, still some calculation issue. Okay, if I will not find it for a long time, then we'll just move on, but let me try to find. So kernel 3, stride 1. If any of you see the mistake, you can help me. So 3, 1, 1, then 4. Okay, I already see some mistakes. So the max pool also is behaving the same way as the convolution, but here's something missing. There should be stride 2, padding 1. Right. So then the next one, 3, 1, 1, right? Next one, 4, 2, 1, 3, 1, 1. Okay, great. I believe now it should work. Yep, now it works. So the person who did this, now at least I can show you how to fix it. So just be careful with the numbers and don't add any unnecessary functions. So it actually was not that difficult to fix. The main logical issue was here, which others can also take into account, that in size this is the image size, right? The box size, not the channel count, because channel count is something that you can, as I said, you can change it as you wish without any difficulty, because this is just in the dot product built-in feature. So here the 18, it can be anything you want here, but the green parts are more complicated. And we will also show quite soon how to deal with these green parts. There are some better strategies than just calculating the exact output. Okay, so that's that. Okay, let me switch back to today's session, and yeah, I put in the Jamboard these things. Oh, thanks, I see some question. Graded to 0. Okay, so about graded to 0, please don't worry. I know I have bug in my evaluation system. When I actually, this happened because these people started posting these generated codes, which doesn't make sense, and I was trying to give them, just 1 of 100, and then something went wrong with my evaluation system. Please bear with me, don't worry, you will not get 0 grades. It's just that I need to fix my evaluation system. I started to mark out those people who submit these useless code, and that's why basically happened that, but no worries, I will fix that. Please don't submit useless code. Try to make your own code, or even if something doesn't work, it's better to submit your code rather than try to generate something that doesn't help anyone. It doesn't help you, it doesn't help me, no one. Like, it's really useless. So yeah, let's learn together and make some great research and great products and things like that, rather than just generate code right now. Okay, so that's that. Let me show you cool stuff today. So the cool stuff today is related to very deep neural networks, because what we did so far were not deep. They were just like really few layers deep models. What I want to do is actually to build something like this. Like on the left side, you would have convolutions, spoolings, linear layers, right? Things like that, which are basically VGG. The architecture's name of these type of architectures, they are usually coming from what actually means VGG. Let me try to pull up. Nowadays we have ChatGPT, right? With the search function, probably we can find what is the meaning of that. So meaning of con model. So we'll see if there is any meaning, or it's just like a visual geometry group from University of Oxford. If that's the case, I'm not sure. VGG, visual geometry group. I never cared of that, but basically these are the models that are what we built last time, the convolutions, max pools, linear projections, and so on. In the top, if you notice, in the very top there is a small max pool stuff here, right, or after the first convolution, and then it goes down. On the other side, we have something that works much better, the ResNets with skip connections. And we'll talk quickly about the skip connections, make sure that you understand why they are important, and then we'll implement a couple of those things and make sure that you kind of understand how this goes. So I actually saw so this is the skip connections mathematically and visually. And the way how you place skip connections, by the way, this is not something set in stone, basically. By the way, starting from now, as you survived so far, which is actually not that far, but still so far, you will get more and more interesting content, basically more interesting models, because the farther you go, the better you understand the mathematics. You actually have more freedom to experiment and build your own architectures. The only advantage basically to using the ready-made architectures is that, like in most cases, they are already pre-trained, and you can just use from ImageNet pre-trained models and then fine-tune them to your own cases. But otherwise, you can make your own architectures as you wish, and some of the architecture decisions might be better if you do it yourself. So the idea, what is happening here is if you have the X on the top of the model, and actually there is the X on the top of the model, which is the input, the image, right? What's coming in. So where is that? So this is the image coming in. And in the bottom part we have Y, the feature map which is going out, or the prediction, but in this case most likely this will be just a feature map. And these weight layers, they are just convolutions in 99% of the time, except nowadays many models are based on vision transformers, which we will also look at them. But the vision transformers and the transformers, this is like cheap shot of trying to fix things which are not fixable that way. So because they are very popular, it doesn't mean that that's the best way to do this, and we will see in a second. So and why this works. So this is just like really very simple stuff. It is just like adding the same value to the output of this block of two convolutions with relu in between. And the day why it works, it is basically if I write it down, so let's try to do this. So if I'm having so f of x plus x and d of x, right? So if I'm using the chain rule and calculate the derivative there, I would get the so f of x of dx plus 1. And then if I'm using the chain rule, remember that the final loss will be multiplied by what's coming from the loss function, right? So it will be multiplied by, basically, let's write it d loss, right? And here it will be multiplied by d loss. So I think you already see where I'm going with this. It is like mathematically great way to avoid the vanishing gradient problem. So what I mean by vanishing gradient problem is actually something really interesting. If you try to add really deep convolutional model without skip connections, which is totally doable, you know how to do this now in PyTorch, just make a for loop of 100 convolutional blocks, right? What you will end up having is that the loss function will be on the bottom part of your graph. By the way, the loss function is part of your graph, but only during the training process, right? So then the gradient, the error, will flow from this part up to the input, right? The input is up here, x, right? So normally what will happen is without this plus 1, you will have good gradient here very close to the loss, and the problem is that gradient here, dl up here will be 0 basically when I reach the x, and this will become really strange model because, and this is actually something you can look up yourself, it's called extreme machine learning, I think it was called like that, because this part of your model will probably be random forever basically. So basically something like this will be random forever, and here you will have some learnable part of your model because of vanishing gradient problem. And then for the ResNet part, you will never have this problem because just of this very simple mathematical solution where you add the input to the next layer, it will just work forever great. So you might have one question here, like if I'm having the convolution plus the input of itself, then it will not be very efficient because the image will be huge resolution here, right? At the end, it will be the same resolution here, but it's not the case. So what's happening here with these dotted lines, these are the, how it was called, so we have skip connections and we have bottleneck connections. So the bottleneck connections will be having in this part of this dotted line additional convolution. So you can imagine that instead of identity here, we will put an additional block of convolution there, and in these parts we will reduce the size. So again, this will be reduced sized until again the same size here, until this part where we will reduce again the same size going on, and then reduce again here, right? And every time when we reduce the size, we will increase the channel count, right? But in these middle parts where we have the simple skip connections, the channel count stays the same all the time. Okay, so that's that. We'll get to the coding part also soon. Maybe you have any questions in the chat. Okay, good. Maybe not good that you don't have questions, but anyway, like if you have some ideas, thoughts, something right, then let's keep looking at these things, and then let's code them. So another thing you might think is that plus here, right? It doesn't feel too logical. You might think that maybe a better way would be if I have some output of image like that, and if I have the skip connection previous image here, maybe I should not do the output, but I should concatenate them, right? Like concat them together using the torch stack or something, right? And then pass to the next layer. What actually researchers have found, and it has been repeated many times, concat, is that this is the performance of concatenation of these outputs is exactly the same performance as having the plus here, basically, but having the plus here is much more memory efficient because you just don't have new matrix here, but concat will fill your GPU very fast. So that's something to also keep in mind. Maybe it'll come back to you later, but it has been tested many times that the just simple plus is enough to have this result, and specifically because of the derivative, right? So that's that. What else? Let's look at some other examples. Right. Before coding, maybe we should look at something more interesting. Okay, let's look at bigger picture. So regarding why we need actually this, so why we cannot just stick with VGG. So VGG, those models, right, which are just having this vanishing gradient problem. So if you look at the ImageNet accuracy and the performance characteristics, so these old models like VGG, they are the worst ones. So that's one reason why not use them. Then the ResNets are much better, and it depends also on what kind of ResNet you're using, because some ResNets which are deeper really works much better. So basically there's also really interesting thing that with the skip connections, you don't have vanishing gradient, and you have ability to make super deep models basically, and the bigger, larger models and deeper you make, the higher accuracy you get. And what means this ResNet 18, 34, and so on? It means just how many convolutional layer, or just the ResNet blocks you have. You will see that the ResNet block is what it means is it is the whole stuff together, like convolution with the skip connection. That is the ResNet block. So the more blocks you make, the larger hidden sizes you make, the higher accuracy you get. So that's that. Then what else? So we have the EfficientNet, and EfficientNet will be something that you will actually have. I think that's a great achievement. Basically, you will be able to take the EfficientNet paper and being able to using my template just to implement it yourself from the paper, because there's nothing difficult there at all, and it is very similar to ResNet. It's just have a different type of block with depth-wise convolutions, and the accuracy is really good. So basically, compared to ResNet and VGG, the accuracy, and even to the vision transformers, the accuracy is better than some of the vision transformers. By the way, the EfficientNet, which is just the convolutional model. And then also keep in mind, it's not about just the top 1 accuracy. By the way, top 1 accuracy is always what you need to look for. Top 5 means the accuracy in between the top 5 predictions, which is, there's a lot of AI related metrics like mean, average, precision, and so on, which are not really great metrics. So it is always better to look at the worst metrics for evaluating your stuff. The another thing what you need to look here is how big is the model. Like for example, EfficientNet, very small model. ResNet, even smaller model. The VGG, very large model, and the transformers, vision transformers, huge model. So the vision transformers will fill your GPU immediately full, where the EfficientNet transformers and EfficientNet models and ResNets are way smaller. Then also the inference time, right? How fast it is. The EfficientNet is super fast. The transformers are very slow. So basically, you need to keep in mind all of those things, and that's why still skip connection based convolutional architectures are great, and even transformers use the same skip connection architectures in their approaches. So that's something to keep in mind. Okay. So we have been talking about this for a while. Okay, let's try to do some code example with ResNet skip connections, and then we'll have more interesting architectures as well to look at. So let me share the 9.2 template in Moodle. And if I'll have time today, or maybe next time, because now I'm not in person, I will show you how to use also pre-trained models in from Torch Vision or Hugging Face. So you can normally, how this is done, you find pre-trained model and you fine-tune it to your own needs. But you can also make your own architecture and train it from scratch. It is usually done in a research setting. When you need to do something quickly for production, you fine-tune things. So, but even for fine-tuning, right, you need to understand how this works so that you don't mess up with this. So, yeah, I'm now sharing the 9.2 template. Please get the template. We'll share also the task itself. So it's written, please implement from schema so please implement from schema the ResNet model. We'll see how the schema looks. Okay, it seems about okay. I think it's actually not the whole model, but just the ResNet block. So we'll start with ResNet block. I will show you just in a second in the code as well. So this is the ResNet block. Again, you already are smarter than many people in the sense that you understand that these boxes mean equations, right? So you have convolutional algorithm / equation, ReLU equation, batch norm, convolution ReLU. The plus means addition, right? And this is the whole block. And you will repeat this block, let's say 100 times, and you will have ResNet 100. So that's the idea. Okay, so we have the block, and let's go to the code. So quickly find my template. ResNet, DenseNet. We will try to also look at the ResNet. Try to look at the. So this is the Fruits dataset. Maybe I should copy my data. Okay, I have it here. Look at also the DenseNet and then EfficientNet. The DenseNet is also a really interesting architecture. It helps to understand what's possible. Okay, so let's look at the code. Just a second. Need to share the pie chart. Okay, good. So the pie chart code, right? Okay, so we have the ConNet block, and right, I think this will be okay. Why you have ConNet block? Is that the same? Okay, REST block. Okay, not sure about why we need ConNet block here, but we have ResNet block here. That's for sure what we need. And yeah, let's try to implement this, and then follow along with me, and we'll see what parts are missing and what we need to fill. I don't think we need to fill all of the parts, actually. At least I don't think we need the ConNet block. Okay, let me actually make some notes to myself. Don't know why we have it here, but we don't need it. At least I don't see the point. Just a second. So, do not need ConNet block, right? So yeah, I'm now. Let's look at the ResNet block now. Just a second. Yep, so the ResNet block. Yep, hopefully you got the template, at least I hope. Okay, so let's use just the built-in function. So we have, how many convolutions we have? We have 2 convolutions. So self convolution 1 will be torch n con 2d, and it will have in channels. All right, actually I have something really interesting to ask you. Right, excellent. So hopefully some of you are still alive at the chat. Please, hopefully you are. So what? Let me type in question in the chat. So what combination of stride, padding, and what else? Kernel size allows us to get same size input as same size output as input. So So this is my chat question in the chat. So what I want to see is, please type in kernel something, stride something, and padding something. Any of you know the answer, plus, minus, or if you don't know the answer, or try to type in the answer, please, in the chat, if you hear me. Hopefully you hear. Oh, thank you, Nils. Excellent. I love that somebody is at least paying attention. even if something is wrong, we'll look at this just a second, but we'll check. Maybe it's even not wrong. We'll see. I believe there might be multiple combinations where it works. We'll see. It must be multiple combinations. But the one combination is super popular. I mentioned it once. Yeah, I think Mont is answering what I said here. But basically, yeah. So I mentioned it already once, but we'll see if that's the only. There must be more combinations of that. So this is the formula, the same formula we used before, and this is the convolutional formula which is still important. So let's see. So if I have 28 input, right? And remember, those strange brackets means flooring, right? So 2 times 1 minus 1 divided by 1 plus 1. So that was the idea from Niels, I think. So this is then 30. So this will be 29 divided by 1. So this will not be the case. Practically, it's also never a good idea to do any kind of matrix operations with something which is kernel size 1 by 1. They are actually, I think they were called pointwise operations, pointwise convolutions, but basically one by one matrix works very different than any kind of other matrix, but still, regardless of that, so this will be basically 29 plus 1 equals 30, right? So this will not really be the answer, but but if I put in this standard way, how this like done in many cases, maybe you can now find some other combination which would be nice to see, then it should work. So as I said, there must be some other combinations as well. So let's see. So this is then 30. So right. So this is then 30. Yeah, 27. Right, 27 plus 1 equals 28. Right. So that's why it works. Hopefully it makes sense, right? Because what actually this formula describes, this is nothing like out of ordinary. It just describes how, let's see, can I move this thing? How the kernel moves around the, remember the image? So it starts somewhere here and then use the stride, goes, then goes from the other row and so on, and then produces as an output this new feature map, which is usually smaller than the input, and we need to calculate the output. And why this is super important here is because we need to do this operation plus x, right? And if we have two different size matrices, like here we can see in the middle part these these bottleneck connections. If you have this one and this one, we cannot just add them together, but we can add this one and this one very easily together. Okay, so that's that. Okay, let's go back to the code. So this is the in channels, and let's keep digging. So the out channels is given, and then this magical combination, kernel size. Okay, let me look at something. Yeah, so kernel size will be 3, padding will be 1, and then stride will be 1, but I will use the stride from the input. You see, this is default value 1, And the reason why I'm not just typing 1 here is because I also want to have those bottleneck connections. And the easiest way to do the bottleneck connection is just to make stride, for example, 2. So this will just divide everything by 2 in terms of size, and everything becomes 2 times smaller, basically, in most cases. So that's why I'm using the stride from the input. But this is the 311, basically. So nothing complicated here. So that's that. Okay, let's keep moving. So then the next one, BN batch norm 1. Again, here is also interesting thing. I'm writing these as the member variables of the torch.nn module, and everything that is torch.nn will be automatically differentiable auto-grad, right? As we talked 2 times ago, right? The auto-grad of any learnable parameter. We could also have here sequential list, or maybe so not the Python list, but sequential container, right? Or module list. We can do that, but this will make code less readable. So this is actually a great feature of the PyTorch, that you can write your variables, member variables, as this, and you don't need to specifically notice that here is something learnable inside. But if you do the same thing in the, like for example, if you add this here in the forward pass, then immediately this will be a problem, because forward pass is not something that is, so basically it will not get the parameters function out of there. What I mean by parameters function, if you scroll down, you have optimizer here, Adam optimizer, model parameters. And these model parameters look for these learnable parameters and send them to the optimizer. If you do any kind of additional parameters in forward pass, they will not be recognized automatically. But in many cases, for complicated models, you actually do this here. You will see that there are many models where these parameters are defined also in the forward pass, but they are not then used. So they are not the final product then. So they're just used for some reasons. Okay, so that's that. So again, let's use torch and then batch norm 2D. And here we'll have the out channel size. Right, I think that's the only parameter I need. It can be also something else. It can be not only the batch norm, there exists also the so there exists the layer norm, group norm, instance norm. There's all sorts of normalization functions that you can use. They're all really good in many cases. Like some are used for generative models, some are used for recurrent node models, some are used for the transformers, time series. But batch norm is kind of like the main tool for everything, basically. So it is most stable one. So the convolution 2 will have the out channels, and then the output will be also out channels, and then stride will be 1. So this is basically, this kind of combination is, you can have got almost like hundreds of these guys here. So it will not change the output channel. The output channels are not changing. The kernels are, the feature map is not changing. Nothing is changing. It's just adding parameters to the problem, basically problem solving. And actually, to adding parameters to the problem solving helps. So this is something proven, that if you add more parameters, the models get better for free. Basically, something that many people don't realize. And yeah, so this is kind of like scaling laws. You can have labeled data, which is the most efficient way to get your accuracy up. But then if you don't have enough, maybe the high quality label data, you could try to get also accuracy up by just adding more parameters. But you need to be careful and not overfit the model. That's something to be careful still. So batch norm 2. Okay, cool. So far so cool. Then yeah, so then let's define also the bottleneck part. Okay, so how to do the bottleneck part. So if if yeah, so out channels, in channels, out channels. Yeah, if stride. So the stride, I guess, is the only parameter which makes us problems, I think. Yep, so the stride, if the stride is not 1, then I will need the shortcut or the bottleneck convolution, or any operation. It can be also max pull, by the way. It can be, there is no rules that the only convolutions are the best way to do this. This is basically projection. It does not, we try not to do anything, learn anything serious here. We just try to make sure that the size is the same. So convolution, there will be the in channels, out channels, and kernel. All right, this will be the pointwise. Yeah, this is called pointwise convolution. So kernel 1. We tried not to mess up anything there, just to try to do this as simple as possible. Stride, and yeah, that's about it. I think that will be fine. So really, like almost like, yeah, it's not really identity matrix, but still really simple part here. Okay, cool. Yep. So that's about it. And then the output part, the forward part. So for the forward part, for the skip connections, and that's why it's called ResNet, there is a residual flow of data. And this will be really cool that we first have some kind of model where the flow of data is not sequential. So what I mean by that you will see. So out, self, convolution 1, forward, x. Then the next part will be, by the way, we could, yeah, but there is a relu, right? We could actually make all of this sequential. It might be easier, but anyway. So, okay, torch, relu, out. Oh, I forgot the batch norm before. Like, what was in my schema? Right, in my schema, batch norm is after the rel. I know there is a, yeah, so there is a case where some argue that there was a paper actually called, like, I think it was like pre-norm or after norm or something like that, where there were experiments where normalization, location of the normalization function improved the results, but in general it's not really that logical. Why would you want to have batch norm after the non-linear function? So I just want to add note to myself that I need to fix that schema so that batch norm comes before relu. So this is like this version, which was called like after activation. Okay, good. Well, let's try to make it in the way how I would do this. So the batch norm goes first, relu goes after, then the next one, convolution, batch norm. And again, why there are two convolutions and batch norms, this is again debatable. There's no one way why this should be that way. I think the original ResNet had two, but it can be also one, it can be four, it can be something you discover. So there's also a bug here. Out, okay, cool. So this is good. So this is just the simplest part, but then we need to do something actually really cool, which is out plus residual. And to do this, we need to make sure that the sizes of the outputs, let me put it like that, are the same. If the matrices will be different size, this will cause error. And if any time you have problem with this plus equals sign, sometimes PyTorch requires you to do this actually, because the overridden function, this is inline addition, and it might be sometimes that it's hard, sometimes for some technical reasons the autograd doesn't work with that, but just for you to know. So that is that. Then also the skip connection, I mean the bottleneck connection. So sometimes when we have stride 2, this will not work. To make it work with stride 2, we will write self shortcut. So this means if I have the member variable called shortcut, then I want to call it. So to the residual self shortcut forward residual, or X, it doesn't matter, but yeah. But we could actually call it X here. So that's about that part. Okay, I'm just realizing that in my scheme we have relu and batch norm after this part. We can do that, I believe. Yeah, it will work. So let's move that part after, because also this is actually good idea, I did not realize before. But so if I'm adding residual here, it will be better to normalize it and then call relu. Definitely good. Hopefully it makes sense for you at least a little bit. So we'll share this code to the whiteboard. So this is like the first proper interesting architecture that you're doing now with the different paths of the function flow. This will be on the slide number 8. Okay, let's move on to the next part. So ResNet itself. Oh, and I also have this cool function here, which is calculating the model size, the same chart, same table I showed you on the whiteboard with different model sizes. Model size is something that you always track, because it might not fit on GPU, right? It is also making model slow. You also need to make sure that model is large enough. So let me look what were the model sizes. Millions of parameters. So the EfficientNet, so the ResNet was ResNet 50 was 25 million parameters. So I would say that if your model is lower than 1 million parameters, or at least let's say 10 million parameters, then probably this is too small model. So you need to track that part as well, if you want to have good results on image tasks. So that is that. Let's keep digging in. So the ResNet part. Okay, so the ResNet part will have. So let me. Oh, I actually need to open the task. No, I don't have the task for ResNet. That's also interesting. I have only the task for ResNet block, but not for the ResNet schema itself. I need to add here a note to myself. But that's no worries, I will help you. Okay, so let's try to make it ourselves. Okay, let's try to improvise a little bit. So let's call this the same way as we did with the previous model. So this will be encoder, and this time, because all the skip connections are in our blocks, we can actually use sequential. Torch and then sequential, and this will just make our life easier, because we will be able to write them one by one down. So okay, so that will be, I think my original architecture is something from the original paper. Let me look, maybe I can find the original paper of the ResNet. Okay, well, forget about it. Let's just write it. So torch and n convolution 2D, and what we could start working with is we could just make the first kernel. Usually in all of the models are a little bit larger than the next ones, because all of our internal kernels are actually 3 by 3. So the first one we could have 5. Oh, not the channels, but kernel. So the in channels will be 3 actually, because we have colored images. Then the out channels, we could already say 4, and the kernel size, let's say 5, the stride and padding 1. So normally for all models, convolutions, the first layer has a little bit larger kernel size, either 5, 7 or something like that. Then the batch norm. All the num channels, num features 4. Then the torch and relu. Great, and now let's pack the res blocks. The res blocks will be the most interesting stuff, so we will just literally use our res blocks here. And we'll just need to define n in channels, which will be 4, out channels, let's say 8. Right, these will be the res blocks. We can add many of them, so let's say 2 of them like these. Then we can add these, what we call these bottlenecks. So the bottlenecks will be parts where we will change the channels count and increase the stride. Okay, let's do it a different way. So let's keep here 4, 4, 4. And every time when I increase the channel count, I will also do the stride. So this will be the bottleneck. And as deep as I make this model, it will not have vanishing gradient problem, because there is always this skip connection. So 8, 8, 8, 8. Then let's make another skip connection. I mean the bottleneck. 8 to 16. And then add more 16s. You can also have this as a for loop with configurable layers, right? So this is also the way how often this has been done. So this will be much deeper model. And imagine each of those res blocks already have 2 convolution layers, so everything is twice as deep already. So 16 to 32. Okay, I will not make it much deeper than 32. I also need to be aware of that I don't make it, because the input image is really small in our case, that it doesn't go under 1 by 1 dimension. Okay, and at the end, let's do something really cool. So before we had to calculate the size, right? Okay, let's leave it like that. Yeah, so before we had to calculate the size of the last layer, right? I will show you one more trick how to do this without calculation. So let's see. So this will be classifier. Sometimes in the built-in models in the Torch Vision, they also have the same naming as encoder and classifier, because this will be the part which you will fine-tune when you will have your specific task. For example, you will train both of these parts for the ImageNet, and then let's train only this part for the classification of the, let's say, cars, or classification of the damaged parts in factory or something like that, you will just train this part and not touch this part. So there are different ways how to do this, and this is called transfer learning, by the way. So then here in this classifier, we'll show you that trick. So linear will go in features 32, but I just realized also that I need to reshape it. Okay, so let's call it, we can call it classifier, but let's not make it with sequential. Len dataset full label. So this is how many fruits we have. Okay, so then here the execution. So this will be really simple. Out self encoder forward x. Okay, great. And then the trick comes. So the trick is really cool stuff here. So the trick will be using the so this is torch. Let me write the whole stuff. Torch and end functional adaptive. It can be also max pooling, but it can be adaptive as well. So adaptive to the pool, that is really powerful function. So what it does, it takes our feature map, and it will produce the necessary output size of what I will ask it to be. So in this case, output size, I could have 1 by 1. So so this is actually not that rocket science type of function. It's what it does, it is following. So I will give the for the formula what is out size, and I want in this case out size to be 1 by 1. So imagine if we have here the batch channels with height, then after this function we must have batch channels 1 by 1. And what it does, it will find the kernel stride and padding which will make sure that the output is 1. So this one might not be the optimal combination of those, right? It might have the stride, I think it will not have stride 4 or something extreme as that, but it will try to make stride as small as possible, but it will still find the kernel stride and padding so that this will execute in that way. Hopefully that makes sense, but this is really cool trick to not have this calculation all the time, what is the exact size of my feature map. So this is commonly used. It's called adaptive average pooling at the end. So that's that. Then what we will do, we will reshape it to the sausage type, right? The vector type. So out view, and there is in the let me write down. So there will be out size. So this will be the batch size. Maybe just for the clarification, I can write it down. Batch size. And the other part will be just the channels, basically. So in this case, the channels will be 32. So yeah, I believe it should be like that. Yep. So the view is something that we use when we have continuous matrix, but if the view doesn't work, you can also use reshape. But reshape is not good because reshape will copy memory from one part of the GPU or the RAM to the other part, but view will not change the pointer addresses. So that's the difference here. Oh, okay, it's scared that you're saying that you don't find ResNet. Okay, sorry, I did not watch the chat. I will double check just a second. Hopefully you followed so far. Maybe you wrote it somewhere, but I'm now a little bit scared that maybe I shared you wrong template. Let me check. Anyone else also have the same problem? Let's look. ResNet template. Let me look at that one. No, I see ResBlock and ResNet model. Maybe you copied yourself, unfortunately, wrong template. Just double check that you're using the right template now. Maybe I can share in the chat as well the link. Let me find. At least I just copied from what I shared with you, and it seems that that template is the correct one. Okay, good. Okay, so Mont says that this is the correct one, but I shared right now as well in the chat. But if you missed out, maybe just follow along and then fix it later. So this is then the out size. So now as soon as we do that, we can easily call any linear function. So now it will be out, forward, out, right? And we have linear, and at the end, if this is a classification task, of course we need to have the softmax, so out, and the multi-class, right? If this is binary, then we need to have sigmoid. So torch softmax out, and dimension will be 1. Okay, and why I added here the batch size and not just wrote batch size from the constant up here is the thing which I told you last time, is that when I will use this model in real life scenario, I will not have batch size, and I need to have what is the real batch size here. That's also one thing that is with regards to what I showed you in the very beginning with train and eval modes, right? So okay, so this is it. We'll see if this whole code works. As you see, it's not really that complicated. Really, there are basically literally maybe 20 lines of code for all of this. You just need to understand how this works, and then you're free to experiment with many different like combinations and architectures. There's also DenseNet architecture, the EfficientNet. There's like all sorts of interesting architectures. We'll look at some. Okay, so let me try to run it, and then I try to also run this on Google Colab. Okay, something is happening. I'm not sure what. Oh, this is interesting. Oh, right. This is even funny. Okay. Yeah. So Python, so let's fix ResBlock. So even though Python is really loosely typed language, right, weak typed language, even if I can not have some of the attributes defined, I should probably define it. Define them so that they at least don't crash. So here, let's write like this, none here. Okay. So I will also put this on the jump on the whiteboard, this small change. So I could fix this in different ways as well, but this would be I think the most cleanest way. So this would make sure that the shortcut variable in the attributes in the member variables, there always exists, but sometimes when we don't have that skip connection, it's just none, and when we do have it, then it's a function. It is actually similar to some design patterns. So like for example the observer pattern, where you have pointer to function. Okay, so now I'm trying to copy the whole code also into the Google Colab. Let me show what I'm doing there. Maybe it will not work, hopefully it will. So runtime, change runtime to GPU. Again, this is great way to learn for working with CUDA. Again, the same trick here. If you have CUDA GPU, if you have computer with CUDA and you're trying to do this stuff, you will immediately get device CUDA and all of the dataset. If you are doing this at home with the GPU computer, then please change this to maybe 200. This will make sure that you can debug your code. When you're actually trying to run this, then change it to 0, because you see here, oh, it's actually not taking that in account at all. Funny. I need to do another note to myself. I was thinking that that part is implemented. So now it seems that whole dataset is processed regardless. But maxlen idea, like last time in the session, was the idea to cut a little bit down your dataset so that you can debug it. Okay, let's fix this. So this is just for debugging purposes. What I want to do here is like this. So if this is hack basically, so hack. So if I have a maxlen something larger than 0, then return maxlen. So I'm pretending that my dataset is really small if I don't have CUDA GPU. So I will not get great results, but at least I can debug and test that everything works rather than just wait forever for training, especially on CPU, which is on CPU you don't train models at all. Okay, that is actually excellent, because now when I run it, I get the error and we can fix it. Oh, train test split, that is strange. Found input variables inconsistent, right? Maybe I messed it up somewhere more. Oh, I think maybe that's the reason why I'm... Okay, let me find out. There is probably because I added that new stuff here. Maxlen, now something else broke. So the train test split broke for some reason. So this part is len. Why it broke? Inconsistent numbers, that is really strange. How it can get 67,000. Let me add breakpoint here. If you know how to fix it, let me know. Oh, okay, I messed it up myself. So I think in some templates I have this like that. I just did not realize that I have it here as well. So for debugging, here actually is the part where I cut my datasets. So I have 200 by 200, like just 202 datasets. Okay, so let's copy all of this into the Google column. Try to run it there. Oh, okay, if you have errors like that, we can fix that. So I did not realize that I have such a strange things. So matplot tg ag, you can just remove that line. Why I actually used that line was to avoid PyCharm user interface, so that so let me add a note to myself. So remove take something. So that was the idea, so that we have interactive environment, but in the Google Colab we cannot do that. And also then if you scroll down here, there is this plot, draw and pause. So instead of draw and pause, what I want to have here is just show, right? I will add that to Jamboard so you not get confused. So it's just visualization task. Basically, if you change these things around, you will have visualizations that are stacking to each other. And before, what I wanted to do was create visualizations that dynamically change, like in that computer game what we made early on. Okay, so let's see. I think there is one more thing I own. No, it is not. Okay, yeah, just that. Let's try to run it again. Okay, now the dataset is downloading. I want to share with you tonight also one more model, and then we'll leave with some experimentation at home. And next time we will have really cool stuff. We will look at unsupervised learning. So actually you see how fast it goes with proper models. So yeah, and now it's okay. Now it's actually the learning. If you remember last time, it learned quite quickly. If you have deeper models, it will take more time, but at the end you will have better accuracy for sure. So that's what we want. So next time we will look at the unsupervised learning. So what it means is that we will have image data without labels, and we will be able to still classify them basically. So this is like really powerful ways of pre-training or the zero-shot type of models, ray identification, and so on. So actually it fits quite well. There still have lots of mistakes, but we're getting there. Also, one thing which I not showed you so far is to add the augmentations. I told you about augmentation libraries, but in the dataset it would be smart to add actually some augmentations. Even we could get even higher accuracy to this task and even more complex tasks. So I will make note to myself about augmentations. So this is the first proper deep learning model basically, and you see that it converges and gets better and better all the time. Already test accuracy 91%, and we're still getting better and better and better. So let's keep it, I will just leave it running there, and I will show you the next model. I don't think we will have maybe enough time to fully make the next model, but you will be able to complete it later at home and then think about it, and then we'll meet with the unsupervised learning afterwards. So the next model is actually the same thing which we had displayed on the first slide. So this is the DenseNet. So this also allows you to think about how to build models even more complicated, and even there is reason why you do this. There is sometimes that you can have smaller objects transferred, their features transferred deeper in the model. So the idea is that you have not just one skip connection. So this will be just one skip connection, right? But you will have many skip connections. You can have skip connections that goes from the first block to the second block to the next block, and then all of the full factorial combinations that you can have. And in between those, you will have, let's say, some convolution and pooling. So this is like a bottleneck, basically. Bottleneck, bottleneck, bottleneck. And the dense blocks do not change the sizes and so on. The one thing which is very interesting about the DenseNet itself is that that's not only the skip connections, they're doing something more there. So what they are doing there, they're doing the concatenations basically, and concatenations in terms of the channels, if I am not mistaken. So the idea was that I told you in the very beginning that concatenation and addition doesn't matter. I still hold to that because I know that in many models like UNets and so on, it really doesn't matter. But for the DenseNet architecture, they actually do concatenations, and then afterwards, when they have concatenated everything, they reduce the channel count using the So they will reduce the channel count using the I think it was convolution itself, right? Just the projection. So they increase the channel count and then they reduce it in the transition layer. It's called transition layer. So let me find some more visualizations of that. So the DenseNet, dense block. Okay, let's look at one of the dense block stuff here. So this is the dense block. I will open the task a little bit in a second. Maybe I will look at that more. So there is the input, batch norm, convolution, and then of course maybe it's difficult to see here, but basically you get the outputs of these convolutions, which are 3, 1, 1, 1, so it doesn't change the size, and these outputs get all the time concatenated here, concatenated, and so on by the channel dimension. Basically, I think you understand the idea. So if I have in here the RGB image, right, in the top part where I have the channels 3, right, RGB, then after every operation of this I will have more and more channels, like there will be 4, and then there will be already 5, and so on. And then there is the other layer, which I don't see it here, but let me look. It's called transition layer, and transition layer's task, which is in these between those other layers, and it can be actually in the first image which I showed you, those transition layers were where the where I lost. In the first image I showed you, the transition layers were the using the max pool, and here in my task you're actually using the average pool. The average pool, in my opinion, works better, but at the same time the max pool also have some ideas. As I said before, let me explain about max pool, why it's actually cool. So if I have image of like let's say there is grass, and there is in one corner small rabbit, and basically my small rabbit is located somewhere here, for example, right? So the image, this max pool will pull this part like a focus point out here, and this will help us to recognize rabbit faster. Instead, if I will use just the average pool, it will recognize the rabbit slower. So that's also the max pool sometimes is advantageous, but at the same time max pool is less stable than average pool. So here with the average pool we will reduce the size of image. If I had large image, now I have small image, right? That's one thing. And with the convolution, before we had like tons of large images, not just RGB, but channel count like 5, whatever. With this one we will reduce the channel count. Now we'll have again, let's say, just 3. So that is the idea here. First one, this reduce the channel count, this reduce the image size, and then we will repeat again this complicated concatenation procedure with many skip connections. And you just need to be very careful, keep track of what is concatenated with what, right? And if you keep track of that, it is not that difficult to implement. Maybe I can help you with the first part, so I can help you to implement at least let's try to implement the block part, and then the whole architecture will be really easy for you to finish up. Okay, so let me check in the chat if you are still alive. Okay, some are still alive, and somebody is already saying that it's good working. Okay, that's great. Okay, let me just show this last piece, and then we'll wrap up for the day. Okay. So dense block and transition layer, and then DenseNet here, right? So how the dense block might look like. I will try to help you out with that. So again, so we'll have again those the same kind of so the same kind of idea with conv1 and batch norm 1 and so on. So maybe we can split them out or write them together. Okay, let's write them together. So batch conv1 batch norm 1. I don't have parameters here, which is not great. The one thing is interesting. There is so the output will be naturally increasing basically because as soon as we concatenate them by the channel dimension, it will just getting better, getting larger and larger and larger. I'm just thinking what would be the best way to do this. Well, let me wait. So let me figure out. So the in channels we actually could push in. So in channels, and depending on the size of the layer count, basically the more layers, the larger channel count will be in the output actually. So let's start this one by, okay, we can start with anything, but okay, let's start with okay, let's not define it. So this will be the in channels. Okay, the in channels, that's cool. So then the out channels, we need to be very careful. First of all, the out channels for the convolution will be the same, 331. But then the batch norm will be something different. So the batch norm here will be the in channels. That's good. And because of the way how we will chain this together for the next layer, this will not be the same. So for the in channels here, I'll try to make it the same, but it will not be the same. Okay, so this will be twice as large already. So this will be times 2. And then I will try to reduce it back to the same size, otherwise it will become exponentially large. And then here this will be times 2. Yep. And at the end the result will be if I have 4 pieces of these, there will be 4 times larger. So here will be then so for the next part we'll have times 3 back to the original size, and this will be 3, and this will be 4 times and 4. And here need to be noticed that, maybe I should write it here, that C channel output will be 4 times the channel input. And this will be just our configuration. We could actually, I think the DenseNet implementations usually have another parameter which defines how many blocks we want here inside there. Okay, so that's that. How then to chain all of this together? So let's try to do this. So there will be out. Maybe I should actually write it like out1. And now, maybe it will not be the nicest. Okay, well, let's write it step by step. So step by step. Okay, let me think. So batch norm, now we have the first batch norm is the channel count. Great. Let's do this properly. So conv1 forward x, then batch norm, then relu. Oh, I forgot out 1. Okay, good. So this is good. Oh, this is good. Okay, so this is the first part of the chain. Then we'll do the second part of the chain. Out 2. Oh, before out 2, we'll also already have the. So we'll chain with the out 1. How we will chain with using the concat. So out 2 torch cat. Oh, cat is just combining 2 arrays together. So x out 1. The important thing is that width and height doesn't change, and we have stride. We have kernel 3 stride padding 1 stride 1. So this ensures that we can do this kind of crazy thing. So otherwise it will not work. So out 2 goes here, goes here, goes here. Then we will try to do out 3, and this will be the chaining together out 2. So you see how skip connections become more and more complicated, right? But you can like build your own architectures as well. This just allows you, shows you how flexible all of this is. I will give you these schemas for the homework, and you will be able to finish up this. So this is out 3. Out 4. Visually with those arrows it's easier to follow, so be careful you use the right variables here. 3 4 4 4 4 4 at the end. Output out. So the only thing is that out 5 actually contains out 4 itself, so it means we'll have another one. And now let's see, so we have x as an input, 1 2 3, so it's actually 5 times larger. Okay, my bad. So it seems that the output is actually 5 times larger than 4 times. So you can already see that the sizes doesn't change, but this is 5 times larger. So let me share this piece of code to the Jamboard. Oh, to the whiteboard. So this is the dense block. If you carefully follow the instructions of the schema and the architecture, you will see that these skip connections work out that way. So I will add this to the slide number 13. And finally, just if you don't have time now, then you can watch this later. Bear with me, I will add the transition layer here, because that will also be maybe not self-evident for some. Because what we want to do there is to as I said, reduce the channel count, so that in channels will, in this case, what will be, so if there is, let's say, 3 channels, then it's 5 times larger, so there will be 15 channels, and then we will squish it down back to something smaller, let's say 8 channels, like this. That's the point for the transition layer, and also reduce the size of the image. So from one side, if it's not also that complicated, we will have the convolution, just one convolution. Let me just copy that stuff. So the convolution itself will not change the image size. It could change the image size, but we don't want it to change the image size. So the in channels, out channels, and we can again make it 1, kernel 1. Great. Then I think it was also batch norm and relu there. So self batch norm, torch and batch norm, and this will be the out channels. And what else we need? We need pooling. So again, you can use average pool, or you can use the max pool. And here in this case, we want consistent pooling, not the adaptive one, which I showed you before. So where you are, average pool 2D. And how to make it consistent is just choose parameters here which are consistent. Stride to padding 0. For example, that. I hope that this combination is correct one. Maybe the padding needs to be 1. Needs to double check. I will double check and then post the image here to the whiteboard. So that's that. And then you need just to chain all of this together. So out self convolution x, out self batch norm. Whoa, I forgot to write forward, out, then relu. I think relu, was it relu? Yeah. So out torch relu out. Finally the reduction of the size. Self by the way, the average pool, so this is strange. Why do I need it there? Let's not do it in this way. I don't like it. So let's move it here. Torch and functional, because it's not learnable parameters. It doesn't need to be there. Average pool 2, out, kernel size 2, stride 2, padding 1, padding 0. So this would be the transition layer, but let me quickly double check if the formula is right. So if I go back to formula slide, so let's imagine that I have 28, padding 0, kernel 2, stride 2, what I will get, so 26, so 26 divided by 2 plus 1. I don't like that formula. Kernel. I think there was a better formula. I think just from top of my mind, it was stride kernel 1, stride 2, padding 1. Let me check that one. So stride 2, kernel 4, 1. So this will end up being so 226. It doesn't make much difference. Divided 13. No, but the other one also worked actually. So yeah, so this also works, but the previous one also works. So stride 0, 1. So this will produce twice as small image for you. Okay, great. So that is good. So I'm adding this to the whiteboard, and then I will add in the Moodle some final task for the for this DenseNet, right? And maybe like just not make your life too difficult, just please finish up the DenseNet and look at the EfficientNet. EfficientNet might be some additional task for some of you who feel comfortable already with these things, but otherwise don't be pressured too much to do that one. Just finish this one, okay? So yeah, so that's it for today. Sorry for all of the circumstances where I cannot be in person and I'm a little bit sick. We'll try to do these things like the next time. The unsupervised learning, really cool topic, and then we'll start to move to time series, the more generative models and things like that. Okay, that's it for today. Bye bye. Wait, next lecture. Yeah, please check when will be the next lecture, because next week I also am not in Latvia. I will try to find a time slot that works for most, probably also in the evening. Okay, so please keep in touch, and again, don't give up with these tasks, please. And like if you're ready for research for bachelor thesis, master thesis, reach out and